Now, before I proceed with another example for Clairaut's theorem, let me finish chain rule first, because this one is also very important. So I'll just have to discuss it first. So what we have for our chain rule of partial derivatives is simply that if you have an expression, for example, this one, x squared plus 3y, and then this x and then y is actually given in terms of another independent variable, let's say t. So this one is expressed in t, and then this one is expressed in terms of t and z. So you can actually differentiate that using this general expression. So the total differential is actually like chain rule, in a way that there are more variables than what we have. And then we don't have any intermediate variables in our total differential that we have. But in this case, we do have. So for example, we call this x and y the intermediate variables because they are something like giving the intermediate value for u and then for the t itself. They're like, if you have something like a mediator in an agreement, or a referee in any fight. So these variables act like those persona. So the expression is like this, and this is a very general. I want to show you something as we solve this first problem. So I'll be copying this. So let's first construct what happens in this expression. So for number 1, we need to find the partial derivative of u with respect to t. And then this is our expression. Now, we need to find the expression first of our partial derivative of u with respect to t. And in this case, that is simply equal to, of course, if you have the partial derivative of u with respect to x, we need to take the partial derivative of this u first with respect to x. And then we need to change this x in terms of t. So with that, by chain rule, we know that this will be multiplied with whatever derivative of x is here. And then we know that this is actually dx over dt. Because in this case, if we need to try to differentiate x, we'll be able to get the expression with respect to t. And then we add, of course, the partial derivative of u with respect to y. But then again, this partial derivative of u with respect to y has a derivative of y with respect to t. But instead of using dy over dt, we'll be using partial y over partial of t. Why is that so? The reason is that this expression is actually not a pure function of t because we have z right here. Remember, we have z here. So when we try to express derivatives in terms of the Leibniz notation, once we have an expression that is not a pure function of this expression, pure function of the other variable, then we need to represent that in terms of the curly d instead of the the Leibniz notation of the d itself. This one is capital, the normal d that we use, that's d, not the curly d, because x is a pure function of t, and that's what we're looking for. But in this case, because y is a function of t and z, and it's not a pure function of t, then we'll be using the curly y instead. So if, for example, we have something like, let's say z is equal to cosine of t, and then, of course, we have something like plus z here, then we add another one here, that's partial u over partial z, and then times we have dz over dt because z is a pure function of t instead of using the curly d. Okay, so I hope I made myself clear on that discussion about this dx and then the curly y. Okay, so how about this one? Should this be something like du over dt? Because as you can see here, we have x and then y. But remember, this expression is given as if it's not a pure function of t itself because we have z here. So as long as you have another variable situated on the other equivalent of the intermediate variables, then you cannot say that this is actually the total differential. That's just still the partial derivative of that variable. Anyway, so we proceed with the differentiation. So we need to first find the partial derivative of u with respect to x. So that is simply 2x. Then we multiply this with the derivative of x with respect to t. So that is simply equal to e raised to negative t and then times negative 1. And then the derivative of sine h of t is plus cosine of h of t. Okay, so that is the expression for our first term. And then we add, so this one is for the first term. Then for the second term, we have partial u of partial y. So we have 3, and then we multiply this with the partial y of partial t. So that's actually product rule. So we have here t squared times the derivative of sine of zt. So that's cosine of zt, and then times z, and then plus we have sine of zt, and then the derivative of t squared is actually 2t. Okay. So with this, we can rewrite the partial derivative of u with respect to t in a way that it's negative 2. I think I'll be using 2x e raised to negative t. That's okay. And then that's plus cosine of h. This one is supposedly be multiplied. Okay. So we have here a bracket. So let's actually write this one. So I'll be writing this 1. So we have 2x times cosine of h t minus e raised to negative t. Okay. And then we have here plus, I think that will be 3, and then zt squared or t squared z, or whichever, cosine of zt, and then plus 2t sine of zt. Okay, so this is our answer for partial u or partial t. Now, for example, if the problem says that you need to express your answer in terms of t and z only, so we need to find the value of x in terms of t right here. So we know that the partial u or partial t will become 2 times x. So x from this expression is e raised to negative t. So that's e raised to negative t, and then plus sine of h of t, and then this expression. Now this is the 2 final expressions that you can get. So this is actually depending on the instruction, because if the instruction says that you need to express this in terms of t only, then you have to do this simplifying or redefining or substitution to your answer. But how about the z that you can see right here? So you can't do anything about it because that's a variable that is not included in the intermediate. It's not a variable that has a direct relationship with u, so it will just be left out in that expression. But the x here was substituted with the value of x from this original expression, because we need to substitute that with respect to t because we have the equivalent of that expression. So if, for example, it's 2x squared or ln of x, so you just have to substitute x from this expression. Okay, so the answer from our given is, so this is the answer from our module. So you have 2x and then cosine of ht minus. This is actually the answer that we've obtained in this expression. But as I have told you before, if the problem asks you to simplify this further, then you'll be using this as your final answer. Okay, so let's move on with the next. Now let's have this item. And it says here that if we read this expression, it means that we need to multiply the partial derivative of u with respect to t to the partial derivative of u with respect to z. So this expression doesn't mean that we take the higher order derivative in a way that we take t first and then z. So it means that we need to multiply the partial derivatives. This expression is not equal to the partial derivative of something like this. They have actually different expressions. So anyway, let's proceed. So partial u with respect to t, and we know already that we already obtained this expression before. This is the expression for partial u with respect to t. And then we need to take the partial derivative of u with respect to z. And in that case, if you need to find that, the partial derivative of u with respect to z can be obtained from a path where we move to the intermediate variables and then select where can this partial derivative of z be found. So to visualize this, if we have u, you can always do the tree diagram. So if you have u, and then this u is the expressed in terms of x and y, because that's the expression of u here. You can see that there's an x and then there's y. And then for x, we have t as the variable. So we only have t for x. And then for y, we have z and then t. So the tree diagram goes for z and then of course for t. So if you want to find this u with respect to z, you start with u and then you end up with z. So you trace those lines where you would be getting this z. And in this way, we proceed first with the partial differentiation of u with respect to y, and then we move to y and then z. So therefore, the partial derivative of u with respect to z is actually equal to the partial derivative of u with respect to y times the partial derivative of y with respect to z. And in that way, you can see that we have partial derivative of u with respect to z. Now, the magic trick here is that if you try to like cancel this out, you would see that this is the partial derivative with respect to partial derivative of z. But remember, that doesn't happen really in mathematics. That's just it is not an official method that you can do, but it can show you what kind of what's happening, and then to give you the general approach on the final derivative that you will be able to get. So with this, we differentiate u with respect to y. So what we have here is 3. And then we multiply this with the derivative of y with respect to z. And in that case, we do have t as our constant. So that's t squared. And then we have cosine of zt, and then of course times t. Therefore, the derivative or the partial u with respect to z is 3t cubed, and then that's cosine of zt. Now, this is not yet done because the question is we need to take this expression and then we just have to multiply this with our 3t cubed cosine zt. And we've already obtained this expression, the derivative of u with respect to t. So let's just copy that. And then probably we could just multiply it with our expression. I'll just be removing this. So what we have now is this expression, and then we just have to multiply this, okay? So that we have the expression of this one multiplied with our partial derivative of u with respect to z, okay? That is equal to this expression multiplied by this expression. So let me just zoom out. So what we have is this whole expression. Let's make this clear. Okay, so what we have is this expression multiplied with this 3t cubed cosine of zt. Okay, so in this case, we do have the final answer, and this is actually equal to the partial derivative of u with respect to t multiplied with the partial derivative of u with respect to z. Okay, and we can also check that on our answer. So this is the partial derivative of u with respect to z, and then this one is for the partial derivative of u with respect to z. Okay, so we're done with that item. Now let's proceed with another one. Okay, so in this item, what we have is the Helmholtz energy or free energy. This is the general expression of that A is equal to U minus ds, where U is equal to Q plus W. We need to find the expression of the partial derivative of U of A with respect to Q. So if we want to do that using our expression, using the the chain rule of partial differentiation, we know that A is dependent on U, T, and of course in S, wherein U is kind of dependent with Q and then W. So from this expression, we can trace the line So that's it. We can express the partial derivative of a with respect to q. That's equal to the partial derivative of a with respect to u, and then that is multiplied with the partial derivative of u with respect to q. So therefore, we can solve for this. The partial derivative of a with respect to u, so that would be 1, because the t and s would be constant, so that's 1. And then the derivative of u with respect to q would also be 1. Therefore, the answer for the partial derivative of a with respect to q is equal to 1. Okay, so that's a fairly easy problem. And then for number 2, if dq is equal to tds and w is equal to negative p dv, what is the partial derivative of a with respect to v at constant temperature? So what we can do right here is to check on the expression itself and then go back with our original expression. So we have a is equal to u minus ts, and it says here that u is equal to q plus w. So we can also equate this to q plus w minus ts. So with this, if we try to take the total differential of a, we could say that that is dA is equal to dq plus dw minus tds plus s dt. Okay, and then that is dA is equal to dq plus dw minus tds minus s dt. Okay, and then it says here that dw is equal to negative pdv, dq is equal to tds. So with that, we have dA is equal to tds, and then dw is equal to negative pdv. So that's negative pdv, minus tds minus s dt. So with this, we can cancel out tds, and now we're left with the final general total differential of our Helmholtz energies, that's negative pdv minus s dt. And the question is, we need to find the expression wherein we need to take the partial derivative of a with respect to v at constant temperature. So doing that here, we could say that the partial derivative of a with respect to t, I'm sorry, let me just check it, v. So we have v, therefore if we set v being the differentiating variable, we need to take the temperature being constant. So with that, that's a constant temperature. So therefore, we could say that in this case, we've already made the partial derivative of that portion, partial and then partial v. So therefore, this is multiplied with dv in this case. Now, if we would continue that, dA would be equal to this expression. So that's partial a with respect to v, and then t times that dv. And then we could also add, you can also use subtraction, it's just the same way. If we do negative here, then that's just the same doing plus and minus. I'll just show you what happens when you use plus or minus. So if we continue this, the total differential in terms of partial derivatives, that will be plus, and then the partial derivative of a with respect to t in this case, and then we have constant volume, so that is multiplied with dt. Okay, so now that we need this expression, and we can see right from here that these are parallel with each other, also this one. So therefore, we could say that negative p is equivalent to this expression, and negative s is equivalent to this expression. So therefore, partial a with respect to v at constant temperature is equal to negative p. Okay, so this is your final expression, and that's why the answer here is negative p. Now, you can also use negative in this case. For example, you have dA is equal to negative partial of a with respect to v at constant temperature dv. But in that case, the expression would be something like the negative derivative of a with respect to v at constant temperature is equal to positive pressure. In that way, you would be able to get the negative of pressure having the same expression at our final answer. Okay, so that's it for another example of Clairaut's theorem that we applied actually. So just remember, when you have a total differential and then you need to find the partial derivative of a certain expression, or you just need to express this in terms of partial derivatives, what you have to do is to set the expression in a way that one variable is constant. I'm talking about the variable that is kind of independent as well. So you set that as a constant so that you can actually differentiate or express the partial derivative of this total differential. Okay, so I think we're down with the last. This one I think is the most important use of Clairaut's theorem. So in this case, given that we have du is equal to TdS minus PdV, so this is the general expression of our internal energy, we need to show that the partial derivative of T with respect to V at constant entropy, that's S, is equal to the negative change in pressure with respect to S at constant volume. Okay, so let me just give you an idea of how this works. Now, according to Clairaut's theorem, we know that if we take the second derivative of any of these, we know that that would give us the same answer. For example, if we take U and then we do something like SV, we could also say that U sub Vs would just be the same because according to Clairaut's theorem, these two should be kind of equal. So with this, let's do that expression. We need to take the partial derivative of each of them. So we have du is equal to the partial derivative of u with respect to s. So with this, taking it as a partial derivative of s, and this one is also independent variable, so we set that as a constant, so that's v. And then we add ds, and then we have minus the partial derivative of u with respect to v. And now that we set v as the independent variable, we set this as a constant, so that's s, and then we have dv. Okay, so according to Clairaut's theorem, we know that if we take the partial derivative of s, and then we take the partial derivative of this with respect to v, then that is equal to u sub vs. So in this expression, where can we find that expression wherein the derivative or the partial derivative of u can be expressed in terms of the partial derivative of s? But we know very well that this is that portion. This is actually the partial derivative of u with respect to s, and in this case, this is also the partial derivative of u with respect to v. So what we have to do here is to take this out, because that is the partial derivative of u with respect to s. Okay, because we need this as our, so that is our u sub s, and then for the other one we have u sub v, that is equal to the partial derivative of u with respect to v. Okay, so this is our u sub v. But to be able to solve for this, we need to take the partial derivative of this expression with respect to v, because that's the second one. So we have v, so we need to do something like this. Okay, so that's it. And then is it kind of equal to this expression? So we have partial u over partial v, and then we need to take the partial derivative of this one with respect to again, this one is s. Okay, so okay, and now that we've already differentiated this with respect to v, so we need to set the one that's constant now, so that would be s, and then for this one that would be v, because initially we differentiated this with respect to s, so therefore the constant is the volume. But now, since we're differentiating this with respect to v, the constant variable here would be our s, I mean the variable that becomes constant. So that's the same explanation for this one. That's why it's like interchanging v, and then this one now is s. So with this, I can now substitute this with a value from the original equation, which is, again, remember, this expression is actually equal to the temperature, and this one is actually the negative pressure. So with this, we have the partial derivative of this expression, the temperature at constant entropy, that would be equal to the partial derivative of the negative pressure at constant volume with respect to the entropy. So with this, I can rewrite this finally with the partial derivative of t with respect to v at constant entropy, that is equal to the negative of the partial derivative of the pressure with respect to entropy at constant volume. Okay, so this satisfies our final expression that is written here, and we've already proven that using Clairaut's law that we can actually equate these two whenever we have the second derivatives. So remember, you can only do that when you've already obtained the second derivative for each of them, when you interchange these two. For example, we have z is equal to x dy plus y dx. So we can only express these partial derivatives as if z sub x y is equal to z y x. So that's the only way that we can say that these two are equal, and that's the same thing that we did here. It's just that we need to express them in terms of their own partial derivatives. And the difference from this one to this expression is that this expression is actually given in terms of x and y alone. But for a fact that we try to like give this, for example, a dy and then b dx, so the same concept applies. They would just get the same result for the Clairaut's theorem, but of course the partial derivatives would have a and b expressions like this one that we have here. And by the way, we call this the Maxwell relation. So in thermodynamics, this is a very essential property that we should know whenever we talk about gases, and of course the work that is done when we talk about thermodynamics, because there are a lot of cases of systems, may it be adiabatic, constant pressure, constant entropy. There are a lot of things, throttling. So those things, you will learn that in your higher engineering. But I'm telling you, these Maxwell's relation are always kind of given in the exam. It's like find the Maxwell relation for this type of internal energy or enthalpy. And just to give you an idea, we actually have 8 of them. We have the internal energy, we have the enthalpy, we also have the Helmholtz energy, and then the Gibbs free energy. And then within these two, they are actually related to, or related by, the pressure, entropy, temperature, and of course the volume. So with this, knowing all of the 8 the variables that are actually determining factor for any system that can exist in real world, so there are a lot of combinations of these Maxwell relations, and I hope that you study them on how you would derive whenever, and I hope that you study well on how you could apply Clairaut's theorem to derive each of them. Actually, whenever I give exam, I of course give you the general equation because that is to be given. You don't know them. But of course, the relationship, you have to derive that based on the given itself. So for example, dH is equal to, this is not the exact expression, by the way. I'll give you something like, for example, it's SDT plus PdV. So this is not the exact expression, it's just an example. So with this, you apply Clairaut's theorem. So that's simply dH is equal to partial H and then partial of T with respect to S plus this one, okay, and then with respect to T, okay, and then you move forward with the partial derivative. So that is given by H, T, and then V. That would be equal to H and then V, T. So with this, you differentiated this with respect to T, so you move forward with the volume. So we have partial V, and then this one should be something like S, and then that is at constant temperature. That would be equal to the partial derivative of P, now with respect to the temperature at constant volume. So this is the final expression for the Clairaut's theorem of this expression. So I hope that you were able to follow through that. So this is the step-by-step process that you do using that Clairaut's theorem. Okay, so I think that's the last example, and then for the next video, I'll be showing you some discussion about parametric equation, but I'll not be digging much deeper into that because I want to discuss more on the vector analysis. I'll just give you the application of the parametric equation. So once you already know chain rule, or how you can perform chain rule, you already know how to do parametric equation, because parametric equations are just application of this chain rule. So you will not get any problem with that. Okay.